Welcome back to my series that I whimsically call QFT a la Weinberg, where we try to understand Weinberg's quantum theory of fields, his famous, or as some would say, infamous, textbook on the subject. Basically, this is my attempt to understand the subject as laid down in Weinberg's book, and I'm uploading these videos on the net primarily for my own sake, so that 6 months or a year down the line, I will be able to retain whatever I have understood of this book on this reading, so that it may be easier for me to read it the next time around. Anyway, the book, as you all already know, is actually not one book but a series of 3 books. We are, of course, looking only at the first book at this stage. In fact, so far, in a rather large number of uploaded videos, I have only been able to tackle one single chapter of this book. That may be because I have over-explained things a bit. Some of the explanations could definitely have been cut down upon. But as I said, this is primarily for my benefit, and I feel it's better to explain more rather than less, so that later on when I come back to the topic once again, I can remember exactly what I was thinking about or what I understood of the book at that time. Now, as I have just remarked, in all the lectures in this series so far, we have only managed to cover one of Weinberg's chapters. That's his chapter on symmetry in quantum mechanics. And of course, the focus there was primarily in the one symmetry which is extremely important for relativistic treatment of the theory, which is the Poincare symmetry. And we have seen what consequences the continuous Poincare symmetry as well as the discrete counterparts, parity and time reversal, has on a quantum mechanical system. Now, before I resume the series and talk about the next chapter, which deals with scattering in quantum mechanics again, I must address a question which has been asked several times to me by people on the net, which is exactly where is quantum field theory in all this. The question is natural because we have not got to quantum field theory yet. Whatever we have spoken about is basically true for quantum mechanics in general, and the only thing that is vaguely field theoretical about this is the fact that we have focused on relativistic symmetry, and that of course is a stepping stone towards quantum field theory. But whatever we have talked about so far is perfectly general. It can be applied to any quantum system. Indeed, the same is true about the chapter that I am going to discuss next, the chapter on scattering in quantum mechanics. Here also the discussion will be general about all of quantum mechanics. Indeed, we will not enter quantum field theory at all until the chapter after that one, and even there we will do so rather peripherally. It is the 5th chapter of Weinberg's book, which talks primarily about fields and their interactions. And you have to be patient till then if you really want to get into what quantum field theory really is. So in this sense, Weinberg's book is very different from other textbooks on QFT, where you are quickly introduced to quantum field theory near the very beginning. Maybe you get a quick introduction to classical field theory and then you go over to quantum field theory almost immediately. There is a good reason for that, and I hope that by the time we get to Weinberg's treatment of QFT, you will appreciate why it was done in this particular manner in this textbook. But I must also warn you about one thing. Almost every standard textbook that has been written on QFT recognizes the fact that QFT is a very complicated subject. And so, they start with the simplest case first. Almost every textbook starts with the scalar field, because the scalar field is easy to handle. And only then gradually, the degree of difficulty is ramped up and we talk about other kinds of fields and their interactions. Weinberg takes a very different approach. The basic idea here is to treat the theory in full generality so that you can talk about all kinds of fields in one go, essentially as different ways of representing symmetry transformations, in particular the Poincare symmetry transformations. So this has a lot of appeal as far as the mathematical structure of the theory is concerned, but this is really not what you would want to learn if you were learning quantum field theory for the first time. So if this is really your first exposure to QFT, my suggestion would be do not read Weinberg's book, do not listen to these lectures either, but rather read a more usual textbook first. There are plenty available, and once you get some understanding about how to do calculations in quantum field theory, come back to Weinberg's book or the set of lectures. Now, having said this, let me resume the series where I left it off and talk about scattering in quantum mechanics. Much of our knowledge about the macroscopic world actually comes from scattering experiments. Here, what we imagine is a situation where we have particles which are non-interacting very far back in the past, which come together within a small distance of each other at some time, maybe some time which we perhaps call t equal to 0 or its nearabouts, interact with each other, and then they go on their merry way, so that long time afterwards you get to see maybe the same particles as before with different energy and momenta, or maybe even entirely different particles. But the basic feature here is these particles were essentially free particles and non-interacting particles way back in the past, and they will also again become non-interacting particles forward in the future, long time after the interaction takes place. But they would interact somewhere in between, and from observing how this interaction changes the various parameters of these particles, we would be able to deduce a lot of things about the interaction process itself. And that is exactly what we are going to try to describe in the next set of lectures, which deals with this particular chapter of Weinberg. Let us first recapitulate the basic things that we had learned about single particle states in the last few lectures. We have been talking about the effect of Poincare transformations on the state vectors describing single particle states. Remember, a Poincare transformation essentially is a transformation which takes you from one observer to another through a Lorentz transformation followed by a translation. So x mu goes over to x prime mu. These are the space-time coordinates measured by the two observers. And x prime mu is given by this Lorentz transformation, lambda mu nu x nu, sum over nu of course is implied, followed by a translation plus a mu. So when we are looking at the same quantum system from the point of view of two observers whose space-time coordinates are connected in this way, we have a unitary operator u lambda a acting on the state psi p sigma. And the result of u lambda a acting on psi p sigma is the following. Remember, psi p sigma here are 4 momentum eigenstates. The p here is the 4 momentum eigenlabel, and sigma is some other eigenlabel. As we will soon see, the eigenvalue of J3 operator is what comes in here. And the effect of u lambda a acting on psi p sigma is the following. You get a phase factor because the translation, which is of the form e to the minus ia dot p, because the translation is occurring here after the Lorentz transformation, you already have the Lorentz transform momenta lambda p, so it's basically to the minus a dotted with lambda p. Here dot of course means the 4-dimensional inner product. You actually have a factor here which is just a normalization factor. But most importantly, what happens because of the Lorentz transformation is this. The psi p sigma, after the action of u lambda a, becomes a combination of psi lambda p comma sigma prime. So these are 4 momentum eigenstates again, but with eigenvalues with a transformed 4 momentum, which is sort of understandable. But we end up with a superposition of all the different sigma values available, and the coefficients for the superposition are given by these representation matrices dj sigma prime sigma corresponding to a little group element w lambda p. So basically the action of the Poincare transformation on a single particle state has been reduced to figuring out representations of the corresponding little group. Now, as we have seen before, we have to treat massive and massless particles differently simply because the little groups for the standard 4 momenta in the two cases are different. And the result that we had obtained after quite a long discussion is the following. For massive particles, this label sigma would be the J3 eigenvalue, and the effect of a Lorentz transformation would be to mix together states with different sigmas, different J3 eigenvalues, and this dj sigma prime sigma would really be nothing but spin J representation matrices, the 2J plus 1 dimensional unitary representation matrices for rotation. Massless particles are slightly different. There, sigma again is a J3 eigenvalue. We call it helicity in this case. But the important thing is dj sigma prime sigma is essentially delta sigma prime sigma times the phase factor. The phase factor depends on sigma times theta of lambda p, where theta is a given angle of rotation which is there in the corresponding little group element. The important thing here is, whereas for a massive particle, Lorentz transformations mix states with different sigma values. For massless particles, states with different sigma values do not mix. The sigma value does not change because of the Lorentz transformation. Now remember, this Poincare transformation, or just the Lorentz transformation part of it, essentially describes the view of the same state from the point of view of different observers. These are passive transformations. The observers change, not the state. But the wave vector that you use to describe the physical state, of course, changes. But as we have seen, for massive particles, states with different sigmas get mixed up with each other under such a transformation. What that means is basically that while one observer may see the state of the system as having one particular value of sigma, another observer may see other different values. Hence, what we really have is the following. All the 2J plus 1 different states which are corresponding to different sigma values for a spin J representation should be treated as states which describe the same particle. The particle, of course, will not change because somebody else is looking at it. So all of these 2J plus 1 states are different states describing the same particle. For massless particles, on the other hand, the helicity does not change under Poincare transformations, and so you essentially have only one state and no mixing with other states. Massless particle states with different helicities must be different particles. There is a caveat to that which we had already discussed before. Parity changes the helicity sigma to minus sigma, and that is the reason why for massless particles which respect parity symmetry, like the photon, the plus 1 and minus 1 helicity states are considered to be two different states of the same photon and not different photons. In contrast, for neutrinos, which are weakly interacting particles for which parity is not a good symmetry, a positive helicity neutrino and a negative helicity neutrino, a right-handed neutrino and a left-handed neutrino are considered to be different particles. From this, it is rather easy to figure out what would happen to a state corresponding to several non-interacting particles. Now, rather than having a single pair of indices p and sigma to describe a single particle state, for a multi-particle non-interacting system, we would have to have momenta for each particle, the sigma value, that is either the J3 eigenvalue or the helicity, for every particle. In addition, we will also need one more describing index for each particle, which talks about exactly which particle we are dealing with, simply because we could possibly talk about non-interacting particles of several different species at the same time. So for each particle, we will have 4 momenta labels P1, P2, P3, etc. We will have spin or helicity levels, sigma 1, sigma 2, sigma 3, etc., as well as n1, n2, n3. These additional labels which essentially tell us what kind of particle we are dealing with here. And when a state described by all these labels is acted upon by a Poincare transformation, once again, although we say that the state is acted upon by a Poincare transformation, what is really happening is that we are describing the same state by two different observers whose space-time coordinates are connected by the Poincare transformation. When this happens, each individual particle in this essentially transforms on its own. So U of lambda A acting on the state given by, labeled by P1, sigma 1, N1, then P2, sigma 2, N2, then P3, sigma 3, N3, and so on, is given by a rather lengthy looking expression, but if you break it up, it turns out to be rather simple to understand. Just like the phase factor e to the minus I A dot lambda P that we had for a single particle case, here we will have one such phase factor for each one of the particles. The four momenta P1, P2, P3 of the individual particles which make up my state transform under the Poincare transformation to new four momenta lambda P1, lambda P2, and so on. So basically it's e to the minus A dot lambda P1 minus A dot lambda P2 minus A dot lambda P3, all of which go up in the exponent to form the phase factor. The factor which takes care of the normalization, square root of lambda P0 by P0, occurs here again, but you have one such factor for every particle, lambda P1 0 by P1 0, lambda P2 0 by P2 0, and so on. And then you have a superposition of lots of states. In each of these states, the momenta have changed to lambda P1, lambda P2, lambda P3, etc. But you have superposition of all different kinds of sigma values. And the coefficients in front are basically products of the single particle factors that we had. So you get dj1 sigma 1 prime sigma 1 corresponding to w for lambda P1. And then you have dj2 sigma 2 prime sigma 2 for w of lambda P, P2, the corresponding little group element, multiplied by dj3 sigma 3 prime sigma 3 w of lambda, P3, and so on. So basically what is happening is each and every single particle state is transforming on its own, and these transformations together is contributing to the overall transformation of the state. Now, while describing scattering theory, we are not really talking about non-interacting particles. After all, these particles interact among each other, and that is why there is scattering. However, as I described a while ago, in every scattering process, we think of particles being very far away from each other in the distant past, so essentially non-interacting, and very far in the future, again they will essentially be so far away from each other as to not interact. So this kind of transformation rule would be very relevant, not throughout the scattering process, but at least in figuring out what happens to the system very far in the past or very far in the future. And which is why states like these are very, very useful. Now we also need to worry about certain technical things here. One of them is the normalization of these multiparticle states. So if you take two such multiparticle states labeled by P1 sigma 1 N1, P2 sigma 2 N2, and so on for one such state, and P1 prime sigma 1 prime N1 prime, P2 prime sigma 2 prime N2 prime for the other, their inner product will essentially mimic the orthogonality that these states have at the single particle level by giving you products of various delta functions or delta symbols. Because of the fact that states with different P1 eigenvalues are going to be orthogonal, you will get delta cube P1 prime minus P1 delta of sigma 1 prime sigma 1. Also, of course, the two particle species described here must be one and the same, which is why you have a delta N1 prime N1. The reason why we are also talking about particle species as possibly changing is that under relativistic situations, particles can be created or annihilated. You may end up with different particle species at the end state than at the beginning state. So you have to take that possibility also into account. Now the particular normalization factor that we have written down here for a single particle state is something which we discussed at length earlier when we talked about relativistically covariant formulations of our normalization conditions and so on. So if you have forgotten why you have a three-dimensional delta function here, I would urge you to go back and take a look at that part. Of course, you have one such factor for each particle, but that is not all. What is very possible that in the two states whose inner product we are talking about here, the particle labels may have been mixed up in order. The particle which we have been calling particle 1 in this state may appear in this state but as particle number 2 or particle number 4. Particle number 2 on the other hand here might become particle number 3 here and so on. And even in such a situation, you might get a non-zero overlap as long as we are really talking about the same particles but in a different order. Of course, if the two states here had entirely different particle content, or even one particle was there in this state which was not there in this one, you would definitely get a zero overlap. But in case of the particle labels here in the two wave functions being just permutations of each other, you would get non-zero contributions. In fact, you would get similar contributions where you have to add or subtract terms involving permutations. The plus minus sign essentially is due to statistics, whether we are dealing with Bose particles or Fermi particles. Now that is going to be very, very important in the long run, but for the time being, in our description of scattering, at least at this level, we do not have to really bother about whether the sign is going to be plus or a minus. The whole point is you will get an overlap only if the momenta match, only if the spin or helicity components match. Also, the particle species are the same, but it's possible that they may be written in different order, in which case you will again get non-zero values but with possibly a minus sign. Now, these multi-particle non-interacting states are so very important for us that we will need to refer to them over and over again, which is why instead of this rather cumbersome set of labels P1 sigma 1 N1, P2 sigma 2 N2 and so on, we use a shorthand notation which is just use the Greek letter alpha to stand for all these labels at the same time. So psi alpha essentially is a shorthand notation for psi P1 sigma 1 N1, P2 sigma 2 N2, P3 sigma 3 N3 and so on. And the normalization condition that we wrote down a while ago simply becomes psi alpha's inner product with psi alpha prime is something which we write as delta alpha minus alpha prime, which essentially means that you will get 0 unless all the labels match, and 1 if all of them do, or at least a delta function of strength 1 if all of them do. Implicit in this notation is the fact that all permutations are also covered. We are not going to explicitly write that every time, but that's always implied. Now, we have to integrate over the continuous labels P1, P2, P3 and sum up over the discrete labels sigma 1, sigma 2, N1, N2 and so on. And we have to do this from time to time. All of this is encoded by this single integration symbol. When you say integral over d alpha, what we mean here is that we are going to integrate over all the three momenta P1, P2, P3 and so on. So these are actually the three vector parts of the four momenta P1, P2, P3 which we are integrating over. And then we are going to sum up over all sigma values, all n values and so on. Now why is this a dqp integral and not a d4p integral? And what is the difference? Is something we have described in detail earlier. So for the time being, I am assuming that you remember those things, or even if you don't, you can always look them up once again. Now of course these states psi alpha do not describe all possible multi-particle states. These are states we are using P1, P2, P3, sigma 1, sigma 2, sigma 3 as labels, which means they are simultaneous eigenstates of the four momentum operator as well as the J3 operator, or as the case may be the helicity operator and so on. But they form a complete set of states even in the multi-particle scenario, and that is something we express by this formula for the completeness, which here has been written down in the compact form that we have talked about. Any state psi can be written down as a superposition of states psi alpha. The superposition here would be a discrete superposition over the sigma values and the n values, and a continuous superposition over the p values, which has been denoted here by this integral over d alpha, and the superposition coefficients will be the inner product of the state psi alpha with the particular state psi. This is just a generalization to multi-particle states of the standard completeness relationship that we have for single particle states in ordinary quantum mechanics. And this formula is going to be very important in what's going to come. Now, we have already said that if you have a bunch of particles which are not interacting among each other, then under the Lorentz transformation, or in general a Poincare transformation between two observers, the states would change for each particle independently, and that is why we are going to get this product formula that we have just written down a while ago. But the question that we might ask is it possible that particles interact with each other and still transform according to this particular prescription? And the answer is no. This particular transformation law can only work for non-interacting particles, and to see this, the simplest way would be to essentially talk about a very simple kind of Poincare transformation. In fact, a time translation. That is, a transformation where lambda mu nu, the elements of the Lorentz transformation matrix, is just delta mu nu, which means that the Lorentz transformation is an identity transformation, and a mu is simply tau, 0, 0, 0. So you're just doing a time translation and nothing else. The corresponding nu lambda a is simply the operator e to the minus I a mu p mu. And because of the metric that we are using here, remember Weinberg uses the metric minus plus plus plus. For this choice of a mu and p mu, this is simply e to the power I tau times p0, and p0 is the Hamiltonian. So u lambda a, the operator acting on my multi-particle state, not necessarily non-interacting, at least we do not know whether it is non-interacting yet, is e to the I tau h. So e to the I tau h acting on the state psi alpha will, according to this formula, if this formula were valid, give you factors e to the minus I a mu lambda p1 mu plus lambda p2 mu and so on. Here the Lorentz transformation is just the identity, which means all the other factors here would simply go away, and you will not have any superposition. You will just have sigma 1, sigma 2 on this side as well, and p1, p2, etc. But the important thing is, these lambda p's will also be the same as the original p's. So because only a0 is non-zero, and a0 is minus tau, a with a lower index 0 is minus tau, we get e to the I tau p1 0 plus p2 0 plus p3 0 and so on. So e to the I tau capital H acting on psi alpha will give you e to the I tau p1 0 plus p2 0 up to times psi alpha, which clearly shows that psi alpha in this case will be a Hamiltonian eigenstate, and the corresponding energy eigenvalue for H, the energy E, will simply be p1 0 plus p2 0 plus sum of all the particles that are there in the state. Hence, hence this particular kind of transformation will work only if we have a system where the total energy of the system is the sum total of the individual energies, which is possible only if you have no interactions at all between the particles. Of course, this is a bit of a dampener, because in all non-trivial situations, we are actually interested in interacting particles. And this simple transformation rule does not work for such a system in general. Now, on the other hand, as we have already said before, in scattering processes, the particles behave essentially like non-interacting particles very far in the distant past and in the distant future. And in scattering processes, therefore, this simple transformation law will work, however, at times t going to plus minus infinity. Because at these times the particles are too far apart to interact. So in our theory of multi-particle states, even interacting particle states, we will have two sets of states that transform simply. These are the so-called in and out states, represented by psi alpha plus and psi alpha minus, respectively. And These are very important, so let me carefully state the definition. Psi alpha plus and psi alpha minus are states which will be found to have particles described by the label alpha and hence transform the way under the Poincare transformation as psi alpha would if observations are made at times t going to minus infinity and t going to plus infinity respectively. Now, you may have noticed that this is a slightly convoluted way of saying things. Why can't we just say that psi alpha plus is the limit of what the state psi becomes in the limit as t goes to minus infinity, or psi alpha minus is what it becomes in the limit t goes to plus infinity. That is, however, something we cannot do, especially if we are interested in talking about a relativistic theory of quantum mechanics. Now, a relativistic theory of quantum mechanics must be Lorentz covariant. If we insist that our theory be manifestly Lorentz covariant, then one thing we have to do is put space and time on the same footing, and therefore we can no longer talk about time as the parameter in which our states evolve. Rather, we are going to use what is called the Heisenberg picture, one in which states do not evolve in time. And this is why we cannot say that psi of t goes to psi plus minus alpha in the limit t goes to minus plus infinity, because our states are time independent. They don't evolve with time at all. On the other hand, results of observations do depend on time. And in the Heisenberg picture, that happens because operators which describe these observations, they evolve with time. So what we are saying here is, if we were to make measurements in the distant past or in the distant future, our state psi would still be the same then, but the operators would have changed so that in the limit of very distant past or very distant future, the system would behave exactly like non-interacting bunch of particles with the label given by alpha. Of course, alpha, let me remind you, is not one label, but a collection of all the particle labels. And a similar thing will happen if we were to look at the system in the very distant future. Now, in the long run, the advantage that Heisenberg picture gives us of manifest Lorentz covariance outweighs the disadvantage that we are facing right now. The fact that using the Heisenberg picture makes describing these in and out states a lot more awkward than the Schrodinger picture would have. In the Schrodinger picture, all we would have to do is use a state psi which depends on time t, and which, in the limit t going to minus infinity, would go over to a state of non-interacting particles, of the so-called in state for this particular process, and in the limit t going to plus infinity, would have given us the out state, psi minus, for the same process. Because we are using the Heisenberg picture, this simple description is not really readily available to us. There is a way out, however, and that uses the fact that different observers observe the same system using different but equivalent vectors. The important thing is, different inertial observers do not use the same state vector. In particular, if we consider two different observers, one of them, O, has a clock set so that t equal to 0 is some time during which the scattering is taking place. That is, t equal to 0 is the time when the particles are sufficiently close to each other to interact. O prime, on the other hand, is another observer. She is stationary with respect to O, but she uses a clock such that her time t prime is related to O's time t by the relation t prime equals t minus tau. What that means is, the origin of time in O prime clock t prime equal to 0 occurs at t equal to tau according to O. Now, if O sees the system in a state psi, O prime will see a system in another state, which is given by the corresponding unitary operator acting on psi, In this case, the unitary operator u lambda a simply is u identity, comma minus tau. The Lorentz transformation involved here is just identity. There is no relative motion between the two observers. And minus tau actually stands for minus tau, comma 0, comma 0, comma 0. The 4 vector, it talks about the space-time translation. And this operator, u lambda a, acting on psi, has a rather complicated form in general, but for lambda equals to identity, this is simply e to the power minus I a dot p. In this case, a dot p is simply plus tau times h. Remember, once again, that the matrix we are using is minus plus plus plus, and therefore the operator is simply e to the power minus I h tau. So this gets to act on psi to give you the state as seen by O prime. So this tells us that the appearance of the state a long time before or after the scattering event, as observed by O, can be found from the state as observed by O, which itself does not depend on time, by applying this time translation operator e to the minus I tau h, and then taking the limit either tau going to minus infinity for long time before, that is the in state, or tau going to plus infinity respectively. But there is a catch here. If the state that we are dealing with happens to be an energy eigenstate, then applying the e to the minus I tau h operator would only give you an overall phase factor, which would actually lead to a state which is physically indistinguishable from the state that we originally had. This means that in order that these descriptions actually make sense, we cannot really use the energy eigenstates. What we can do, however, is use a superposition of lots of energy eigenstates with closely spaced energies. This, of course, will change non-trivially under the action of e to the minus I tau h. So what we must consider is not the state psi alpha, which is described by well-defined 4 momenta for each of the particles, which of course means that in the distant past this was an energy eigenstate, and it of course stays an energy eigenstate forever, because time translation does not change an energy eigenstate into a non-energy eigenstate. What we must consider instead of that is a superposition d alpha, g alpha, psi alpha integrated over all alpha. Now, let me remind you that the integral over d alpha actually means integrals over all the 3 momenta of the individual particles as well as summation over the discrete indices sigma and n. Here g alpha is a smooth function of the parameters describing the state, and we expect it to be centered around some mean energy of the system, and it would vanish if the energy strayed too far away from that central value. So there would be an interval of energy delta E for the overall system. And G alpha has a non-zero value only over a plus minus delta E region for some finite delta E from this central value of the energy. That of course is P10 plus P20 plus P30 for all the particles taken together. Now, what we are claiming here is the following. If we consider this particular superposition, d alpha, g alpha, psi alpha plus minus, the in and out states, superposed with this weighting function g alpha, and apply the operator e to the minus I h tau on it, you are of course going to get the integral of psi alpha plus minus superposed with a new weighting function g alpha into e to the power minus I e alpha tau. That's simply the result of e to the minus I h tau acting on psi alpha plus minus. E alpha here, of course, is the total energy of all the particles together. Now, the claim is that this superposition has the appearance of the corresponding superposition of free particle states, free particles bearing the correct labels for tau going to minus infinity, for the in state, for the plus sign in the formula, and tau going to plus infinity for the minus sign in the formula. Now, here, I must also mention that although we are saying tau going to minus infinity and plus infinity, all we really need is that this tau become much less than minus 1 by delta E, where delta E is the energy spread, or tau is much bigger than 1 by delta E in the two cases. I haven't mentioned it in this lecture, but I am sure all of you remember that all of this is being done in units where h cross is equal to 1. So, if you wanted standard units, you would have perhaps said tau much less than minus h cross by delta E and tau much bigger than h cross by delta E. So, this is the limit that we are really going to talk about. This is slightly more awkward to talk about than the corresponding statement in the Schrodinger picture, simply because what we have to do is we have to use two different observers, time translated with respect to each other, so that we can conveniently talk about distant past appearances and distant future appearances of a given state. Now, all this may seem a bit too abstract, so let us make this a bit more concrete. A very common scenario when we discuss interacting particles is the following. The overall Hamiltonian describing the time translation of the system H can be written down as a sum of two operators, a so-called free Hamiltonian H0 plus a perturbation V. Now H0 happens to be a Hamiltonian for which we know the eigenfunctions and eigenvalues. And what we are claiming is the following. H0 has the same energy eigenspectrum as H. That is, the eigenvalues E alpha happen to be the same as the eigenvalues for H. So H0 acting on phi alpha equals E alpha phi alpha. The phi alphas, of course, do not match the corresponding H eigenfunctions, but the eigenvalues are the same. And, of course, the phi alphas form an orthonormal complete set. So, using our shorthand, phi alpha is delta of alpha prime minus alpha, and we also have the result that we had already written down earlier, that for any state psi, the state can be expanded in the terms of the phi alpha using the following expansion. Then, of course, is the statement that the phi alphas are complete. Now, before we go any further, let me raise an issue that must have come up in your minds as well. From your study of perturbation theory of quantum mechanics, you would usually know that perturbation, the presence of this extra V, changes energy eigenvalues. In fact, much of time-independent perturbation theory consists of trying to calculate exactly how much the eigenvalue for the Hamiltonian changes because of the perturbation. So how come we are saying that H0 has the same energy spectrum as H? For this, I have to remind you that we are actually talking about scattering states here, states which are not really bound, states in which particles can go infinitely far away from each other and then come very close and then move away infinitely far again. The typical energy spectrum of the Hamiltonian operator relevant for cases like this is a continuous one. So even the shifts due to the perturbation V actually lead to a value which is already there in H0 spectrum. So the energy spectrum of H0 relevant in this case is a continuous spectrum. So you don't have discrete energy eigenvalues, you have a continuous range of eigenvalues. Shifting of the eigenvalue caused by the perturbation V will not shift it to a value which is not in H0's eigenspectrum. It will just move it along a bit and give you a value which is again in H0's eigenspectrum. So, in this case at least, H and H0 share the same energy eigenspectrum. But before I forget, there is another very important point that I should have mentioned, this time about the potential V. We assume that the potential V is a short-range potential, so that when the particles were very far away from each other, in the distant past or in the distant future, the effect of V is negligible. So H essentially becomes the same as H0 in such situation. Then we can define the in and out states psi plus minus with labels alpha as eigenstates of the full Hamiltonian H, that is H acting on psi alpha plus minus, will be the energy eigenvalue E alpha times psi alpha plus minus, and this will satisfy the following condition, that if you take the superposition G alpha psi alpha plus minus with e to the minus I E alpha tau as an extra phase factor which comes in because of the time translation operator, in the limit tau going to minus plus infinity respectively for the in and the out states, this must match the corresponding superposition for the states of the free Hamiltonian H0, that is, the corresponding superposition where psi alpha plus minus is replaced by phi alpha. Note that we are not claiming that the wave functions on the two sides are identical, but we are saying that in the limits tau going to minus infinity and plus infinity respectively, the two sides will match. The left hand side here can be obtained by applying e to the minus I h tau on the superposition integral over alpha of G alpha psi alpha plus minus, whereas the right hand side can be obtained when we consider the action of e to the minus I h0 tau on the corresponding superposition of the phi alphas. Of course, in the limit tau going to minus plus infinity, the two sides will match. Now, because this is going to work for arbitrary smooth superpositions of G alpha, we expect e to the minus I h tau psi alpha plus minus to become equal to e to the minus I h0 tau phi alpha in the limits that we have stated. Tau going to minus infinity for the plus sign and tau going to plus infinity for the minus sign on the psi alpha. And if we just rewrite this a bit, we can write psi alpha plus minus in the following form. Psi alpha plus minus will essentially be e to the I h tau into e to the minus I h0 tau phi alpha once you take the limit as tau goes to minus plus infinity. So if we define the operator e to the I h tau e to the minus I h0 tau as a function omega of tau, this of course is an operator valued function, then the value of omega at minus infinity and plus infinity acting on phi alpha will give us psi alpha plus minus. So this has at least given us a formal prescription for finding out the in and out states corresponding to given particle labels. What you will have to do is to take the corresponding free particle states for the same particle labels and apply on this operator omega minus infinity or omega plus infinity. These are called Moller operators, and we will have a lot more to say about them when we talk about this S matrix in a coming lecture. For the time being, let me reuse this construction that we used just now to prove a result about the normalization of the in and the out states. Consider two similar superpositions of in states or out states. So you are integrating d alpha g alpha e to the minus I e alpha tau psi alpha plus minus. That's one of the state vectors. The other one is a similar integral, but this time with psi beta plus minus, where the corresponding in or out states may be described by other different particle labels, and you are taking the inner product between the two. Of course, these two vectors are e to the minus I h tau acting on this particular vector and e to the minus I h tau acting on this particular vector, respectively. Now, because e to the minus I h tau is a unitary operator, this inner product is exactly the same as the inner product of this vector and this vector, just this much. The important thing is this result is independent of tau. All traces of the parameter tau has dropped out from this expression, which also means that this expression will be the same in the limit as tau goes to minus infinity for the plus sign or tau going to plus infinity corresponding to the minus sign here. But in those limits, notice that our superposition of the in states or the out states go to the corresponding superposition of the free particle or A0 eigenstates. And therefore, this is going to be given by this particular expression. And that of course is integral of d alpha g alpha e to the minus I e alpha tau phi alpha on this side, and a similar thing for this vector. If we expand this inner product and this inner product out on the two sides, what we get is a double integral. Of course, not really double, but because alpha and beta themselves hide a lot of integrals in them, as well as sums, but formally a double integral over alpha and beta of g alpha star g beta times e to the plus I e alpha tau, remember this gets conjugated, minus e beta tau up here, inner product of psi beta plus with psi alpha plus or psi beta minus with psi alpha minus, happens to be the corresponding superposition on this side of the inner products of phi beta and phi alpha. Since this has to work for all smooth functions g, it follows that the inner product of psi beta plus with psi alpha plus and psi beta minus with psi alpha minus must be the same as the inner product of phi beta with phi alpha. That means must be delta of beta minus alpha. So we have managed to prove that the in and out states are also normalized in the same manner as free particle states are. Now these in and out states are so very important in the description of the scattering process that despite the fact that we already have one formal way of finding out psi alpha plus minus from phi alpha, it is quite useful to explore an entirely different approach. This will lead to the so-called Lippmann-Schwinger equation, which will turn out to be very, very useful in the theory of scattering, both in ordinary quantum mechanics as well as quantum field theory. That is what we are going to turn to in the next lecture. Bye for the time being.